the Bohr model of the hydrogen atom. Well, we know that the hydrogen atom consists of a proton of charge E and an electron of charge negative E. And in the Bohr model, this electron moves around the proton on a circle. What Niels Bohr postulated in 1911 was that the angular momentum of the electron is an integer of h over 2 pi, in which h is Planck's constant and L is the angular momentum, and n can take only values integer and positive. It is good to check the units to see that they are consistent. So the unit of the angular momentum is the unit of r multiplied by the unit of m multiplied by the unit of v, because the angular momentum is the cross product between r and momentum. But in this case, r and p are perpendicular to each other. Right? R is the radius of the circle. So if the electron is moving, let's say, in this direction, this will be the momentum p, and this will be the vector r, and they are obviously perpendicular to each other. So this becomes a kilogram, meters, the unit of the radius, multiplied by kilogram, multiplied by meter per second. On the other hand, Planck's constant is 6.626 times 10 to the negative 34 joule second. So joule second is actually Newton meter second, because joule is Newton multiplied by meter. Newton is kilogram meter per second squared, so times meter times second. And this reduces to kilogram meter squared per second, which is, of course, the same as the unit of angular momentum. What does it has to do with standing waves? And we know that in 1924, de Broglie hypothesized that for any particle of momentum p, there is a wave associated with it of wavelength lambda, and the wavelength lambda is related to the momentum p by lambda is equal to h divided by p. So, of course, Niels Bohr could not have talked about wavelengths in building his model for the hydrogen atom, because that was 1911, while the Broglie hypothesis came up in 1924. But now, with a historical perspective, we can look at the entire picture, and we can very interestingly see that these two formulas, Bohr's postulate that angular momentum is quantized, and respectively that there is a wave associated with any particle of wavelength lambda equal to h over p, where p is the momentum of that particle, are actually equivalent. And let's see if that is indeed the case. So L is equal to nh over 2 pi. This becomes Rmv is equal to nh over 2 pi. Angular momentum, as you saw, is Rmv. Or we can continue 2 pi r mv is equal to nh. I'm using this parenthesis here for mv just to emphasize the fact that I want to isolate mv, which is obviously the momentum. So 2 pi r p is equal to nh, or 2 pi r is equal to nh over p, but h over p is precisely lambda. So I can say 2 pi r is equal to n lambda. What does this mean? This reminds us of standing waves, for example, on a string. Remember, we had a string of length L, and if we had standing waves on this string, the fundamental looked like this. The vibration of the string was like this, and in this case we said that the length L is equal to half lambda. This was the fundamental, right? If we went to the second harmonic, we said, when it looked like this, we said that the length of the string is 2 half lambdas, and so on. So overall, we said that the length of the string is an integer multiplied by half over lambda. Well, we can see the similarities between these two expressions. They both involve on the left hand side a length. So here, so the left hand side and the right hand side. For the left hand side, here we have the length of the string, right? While on the other side we have the circumference of the circle. While on the left hand side, in both cases, we have lambda. So it is a remarkable similarity. And this brings us to one important point that I would like to make clear, that when we say quantum physics, the first thing we think of is, well, things are quantized, and this is why it's called quantum physics. And to a certain extent that is true. On the other hand, look at the standing wave on a string, in which we have quantization. Quantization means the wavelength of the wave cannot take any numbers. So if I want to get the wavelength of the possible standing waves on a string, they can take only these values, 2L divided by 1, 2L divided by 2, 2L divided by 3, and so on. But it cannot be 2L divided by 2.3. This cannot happen. So the wavelength on a standing wave is, of a standing wave on a string, is quantized. The same way we can say here the wavelength of the matter waves associated with the electron, they are quantized. So how would that look in a picture? I'm not sure if I will be able to draw a nice picture, but the idea is that this wavelength here, it must look something like this, and if they don't match, I apologize in advance. 1, 2, 3, 4, 5, 6. I need to have an even number of, so it will not really work nicely. I have something on my slides that will work better, but this is the idea that I must have these 8s, right, as I go around the circle. So actually this looks better than what looks much closer to what it's supposed to be. So the important thing is here for the Bohr model is that Bohr's postulate that the angular momentum is an integer of h bar over 2 pi is equivalent to him saying that the trajectory of the electron, the circumference of the trajectory of the electron, must be an integer of wavelengths, the wavelength being precisely the de Broglie, the wavelength of the de Broglie wave. But again, this was postulated in 1911, while this was postulated in 1924. And we'll see in a separate video how we can, using either this or this, it doesn't really matter at this point, because we just showed that they are equivalent. We started from this one and we ended up with this one, right? We started from here and we ended up here. So at this point it doesn't matter which one we start with. We will see in a separate video that this will give us expressions for the radius of the trajectory of the electron, for the speed, and most importantly for the total energy of the atom. And we will see that all of them are quantized. Using this n, the radius can take only values that are given by this relation. In other words, they can take only values that are equal to a certain constant, which is called Bohr radius. We'll see it soon. So the radius, the radii of the electron's path can be only AB, 4AB, 9AB, and so on. We will see that the speed of the electron can take only values, a constant divided by n. So in other words, the speed of the electron can only be a constant, whatever that constant will be, and half of that, and so on. And most importantly, we'll see that the energy, the total energy, can take only values negative 13.6 electron volts divided by n squared. So the ground state will have an energy of negative 13.6 electron volts. The first excited state will be negative 13.6 electron volts over 4. The next one, negative 13.6 over 9, and so on. But for the purpose of this video, this was the point that I wanted to bring across, that Bohr's original hypothesis is equivalent to the Broglie hypothesis, and it is a nice marriage between the Bohr model of the atom and the concept of waves associated with the particle. Let us not forget, this lambda is the wavelength of the wave associated with the electrons. And the second big point here is that quantum mechanics is not necessarily a result of having quantum numbers, because we had quantum numbers, but we didn't call them as such in classical physics when we talked about standing waves on a string or in air columns and so on.